Hello students, this is Dr. Chatfield, and I want to tell you today about the calculations in theory behind the experiment, the absorption spectra of conjugated dyes. Now there's a second video associated with this experiment, and that's on the experimental method itself. Preparing your solutions, really they're already made, and then using the spectrometer. Much of what I say here is in the description, so you can refer to that, but I think it bears discussion, and I'll have a few more details for you. So let me go then, share my screen. So the topic of the experiment is a set of molecules. We have three, A, B, and C. They've got long names that you can find in your lab description. Each of them contains two ring structures connected by a linker, a carbon atom in this case, 3 in this case, and 5 in this case. You'll notice there's a nitrogen with a plus charge here, neutral nitrogen here. Now before we go on, notice that since this nitrogen has a plus charge, the molecule's charged, so there is in solution an anion to balance the charge. You'll also notice that we can write the double bonds this way, but we can also write them this way. So that would be a separate resonance structure. So I've written both resonance structures here. So in any case, the topic of this lab is the spectrum you get when you expose a solution of this compound to UV-vis light. And what you will get when you take the spectrum is a plot of absorbance as a function of the wavelength of light. And it will look something like this. There will be a maximum, and the wavelength of the maximum is, we'll call it lambda max. Okay. Now, before we go any further and talk about the questions we'll ask, let's think about what gives rise to this transition. It's that this molecule has various electronic states. So right here, I've got energy vertically, and these wave functions represent the full electronic state of the molecule 1 and 2. So you might imagine that initially the molecule is in state 1, and along comes a photon of light. That photon has some frequency h nu, and that molecule absorbs that photon, and that increases the molecule's energy, and so it makes a transition from electronic state 1 to state 2. And you measure the frequency of light, the amount of light absorbed, and you get the spectrum. So that's what's going on, and we want to ask two questions about this spectrum. First, is this transition allowed? Now that probably seems like a strange question. You get a spectrum, so there's a transition, it's obviously happening. Isn't it allowed? Well, in spectroscopy, we use the words allowed and forbidden to mean more like strong and weak. So if this peak is a strong peak, it's a strong transition, we call it allowed. And if it's not strong and rather weak, we call it forbidden. And in the course, you'll see why we use this language in the lecture course, but we'll just leave it at that for now. So that's our first question. The second question pertains to all three of these molecules taken as a group. And you'll find that when you measure lambda max for these three molecules, it's not the same for all three, and there will be a trend. And so the question becomes, well, first you have to notice the trend, and then you'll have to ask yourself, is there a simple model that will explain the trend in lambda max, the observed trend? And you're presented with that. Let's talk about it in a little bit, what that model is. So first, I want to talk about the first question. So we've got all this up here again with our transition. This is just floating down here. It shouldn't be there. It turns out that what we use to determine whether the transition is forbidden or allowed is this thing called F. This thing F, that's called the oscillator strength. Now that's a strange name, I know. I'll explain it in a later slide. So just take it for granted for now. And the oscillator strength can be written as an integral over K, which is a constant. It's really a collection of constants, and you'll find it in your lab manual. And of the integral over this thing called the extinction coefficient, epsilon, which is a function of the frequency d nu for the frequency. So let me just write down that word extinction coefficient so you know what it is. You may have seen it before in an earlier course. So the extinction coefficient. There we go. Now you don't have the extinction coefficient handy. What you have is the absorbance, and there's a relationship we're going to talk about in a second. You see, the extinction coefficient is something that that's a property of the compound, irrespective of the concentration of the solution, whereas the absorbance reflects the concentration of the solution. Now, let's just talk about the absorbance for a second. If this were an ideal world, I suppose, in some sense, the transition would happen at exactly one wavelength, exactly at the lambda max. In fact, we know in spectroscopy that peaks are always broadened. They're never just infinitely narrow. And so it's really the area under this, if I extend this peak, if I sort of drew a dash down here, the area under that whole peak then represents the strength of the transition. So we need that area. Now, you'll have to figure it out. And the area, of course, corresponds to that integral. Now you may be thinking, oh, how am I going to integrate this curve? Do I have to do a fit? Well, it turns out that we don't need to know the area very exactly. So we suggest that you do this really simple thing. Draw a triangle, just use straight lines. And then you can measure the area of the triangle, just use a little geometry. The formula is given in your text. And that's going to be the area. And so then that area, and that's going to cover up something. I'm going to have to be careful here. Okay. This area, I'm on erase here. Okay, so that area is going to be the area that you need right here. Okay, so that's all very well and good. Now you might sort of wonder, well, how do I get from area to F? And to get from area to F, what you need is a relationship between A and the extinction coefficient. You need to know that relationship, and the relationship between nu and lambda. Now, the relationship between nu and lambda, you know, the wavelength lambda times frequency is the speed of light, which we usually write with a C, but I'm going not to use C. I'm going to instead use S because we're going to use C for concentration. So that's the one thing. And then the relationship between A and epsilon is fairly simple. So epsilon will be simply equal to A divided by the concentration C times the length of the cell. So here L is length of cell and C is the concentration in moles per liter. So I'll write that down, moles per liter. Length of cell width, maybe is a better, well, L is for length, so we'll say length of cell. Okay. So that's that. Okay, so then you have F after all of that. You'll have to think about how to little calculus to go from d nu to d lambda, but you can think about that. So once you get F, how does that tell you about allowed or forbidden? Well, it's pretty simple. If F is large, by that we mean if it's approximately 1, and that you can think anything between about 0.1 and 1 is, think of that as approximately 1, we'll call that allowed. On the other hand, if F is less than roughly 10 to the minus third, we call the transition forbidden. So now you can see why that triangle is going to be good enough. Okay. So that's it. If you happen to get something that's in between those two ranges, just talk to your instructor, but I think that's what you'll get. One other point here, you might be wondering, what about this shoulder here? Do I include that or not? Well, frankly, you don't probably have enough information to know for sure whether it ought to be included. If that's a shoulder that pertains to the same electronic transition as the main peak, then yeah, you should include it. It could be vibrational substructure, or it might pertain to a different electronic transition, and in that case, you wouldn't include it. And you don't know. That's the bad news. The good news is, whichever area you include, the sort of smaller triangle or some larger triangle, it's clearly going to be close to 1 or in the range of 10 to the minus third, you know. So it's not really going to matter much because we don't have to be very exact. Okay. So that's this whole story about question 1. Let's then go on to question 2, which is about the trend. So there's a molecule, and we're going to have an absorption spectrum. And I want to talk about what gives rise to this absorption spectrum. Okay. So you know about conjugation, and you know that when bonds are conjugated, that the electrons can, the pi electrons can roam the entire region of conjugation. And of course, we've drawn the double bonds in 2 different ways because that's the best we can do with Lewis structures. So it turns out we know that the highest energy electrons or orbitals in this molecule will pertain to this conjugated region. And so we're going to think about our model, our very simple model that's going to explain, we hope the trend will be to think of this as a box. What do I mean by that? I'm going to focus on the region here that these conjugated pi electrons can roam. Now, it's really this nitrogen, carbon, 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 nitrogen. But we're going to extend the box a little bit because the electrons don't just stop at the nucleus of our nitrogens. They can go a little further. The orbitals extend a little further. So this is going to be quite a crude model, but it may just be good enough for us. Now, we are going to focus, our model is going to be one-dimensional, a one-dimensional box. And you might wonder, how could that possibly capture the essence here? And I would say the essence really is that the molecules can roam this entire region. That's really the length. They can't roam from the bonds, away from the bonds very much. So they're kind of restricted to what is essentially a linear region. Okay. Now it looks, of course, it's a zigzag region. So if I just sort of extract that region, it would look like this. And there's the edge of the box right there. But the length that the electrons have to travel is actually this plus this plus this plus this. It's not this. It's not the straight, this as a crow's would fly from here to here. So you can also, if you want, think of straightening this whole thing out, and it would be something like that, and that's the box. Okay, that we're talking about. Now we're going to think about we're going to have a rather crude model for how long this box is. Okay, so we're going to pretend that the length of every bond here is the same. So here's going to be one carbon bond. We'll call that length little l. Another carbon-carbon bond length little l. These lengths will actually, bond lengths, be a little bit different, but not very much. Here's the carbon-nitrogen. That's going to be a little more different. but not a whole lot really. And then we've got that one as well. Okay. So you count those up, and the total length of the box then, I'll use black. The total length of the box, which is L, is going to be 6 times that little l. And a value for little l is given in your lab description. So if we model this whole system as a particle in a box, and it's electrons we're talking about, right? We know the energy of a particle in a box. It depends on a quantum number, n. There are different energy levels. So n is a quantum number, h is Planck's constant. M is the mass. In this case, we're talking electrons, so we can say me times L. Notice we know everything in this equation, except perhaps n, but we know that n has different possible values. Okay, so how is that going to tell us about our lambda max? Because ultimately this will predict lambda max. Well, when my molecule absorbs light, it will be making a transition, as we saw before, and that will be, in this case, between the HOMO and the LUMO. That would be the lowest energy transition possible, and that's the one we're talking about. So let me draw a little diagram. Okay. This will be energy vertically. And we know that the electrons the pi electrons in this system will have particle in a box energies according to this model. And the lowest energy would be for n equals 1. Next one up would be for n equals 2. And then 3. And then 4, and you could keep on going. Okay. Now, the lowest energy possible will be for the ground state. And by ground state, if we haven't talked about it, that's always the lowest energy state, ground state. Lowest total energy. En for energy. Okay, so now we don't have just one electron in the pi system. We have actually a whole bunch. How many are there going to be? It's not just 4. You don't just count the number of double bonds and think 2 in those double bonds. This is a whole conjugated system. And the way to think about it is this. You know that each of these carbons is sp2 hybridized. And you also know that each of those carbons has 4 valence electrons. So 3 of those valence electrons for each carbon will go to form the single bonds, and that leaves, or I should say the sigma bonds, and that leaves 1 left over, which would be in a p orbital, an atomic p orbital that contributes to the pi system. So each carbon contributes 1 p orbital to the pi system. So we have 1, 2, 3 carbons. That's 3 electrons from the pi system from the carbons. Then we have our N plus. Well, N plus will also have 4 valence electrons, so it also contributes 1 electron to the pi system. N, on the other hand, has 1 more electron. It's also in a p orbital, atomic p orbital. Those both get, so there are 2 of those. They both get contributed to the system. So that's going to be a total of 3 for the carbons and 3 for the nitrogens. In other words, 6 pi electrons. Now, if that went a little fast, you can look at the description. Okay. So, according to the building up principle, the Aufbau principle that you learned about earlier, for atoms and also for molecules, the ground state you can construct by putting 2 electrons in each orbital, and they're paired. So there's 1 up electron and 1 down electron. Now, if there were 2 orbitals that had the same energy, then we would call those degenerate, and they would each get a pair of electrons. That would add a complication. So in this case, we'll just say they're non-degenerate. So there we go. This is now the ground state. We placed all of our 6 electrons. So this now, the n equals 3 level, is the highest occupied molecular orbital. That's the HOMO. And then the n equals 4 state is the lowest unoccupied molecular orbital, so it's the LUMO. And when my molecule absorbs a photon of light, here comes my photon, with some frequency h nu. What happens is, if it's just the right frequency, one of these electrons is excited up to the n equals 4 state, and the molecule undergoes a transition, and delta E, of course, is simply E of the LUMO minus E of the HOMO. And of course, because energy is conserved, the energy that the molecule gains is equal to the energy that the photon loses by being absorbed. It disappears. So this delta E of the molecule must be equal to the energy of the photon, pH for photon, which of course is h nu. Okay. So since we can calculate these energies, we can calculate delta E, and we can then determine nu from delta E over H. Okay, so that's what we need to know. So then we can take nu to calculate lambda. Lambda, of course, is equal to the speed of light. I'm going back to C, divided by C. And this would be our lambda max prediction. Really, that's our prediction for lambda max. So you can carry out this calculation for this molecule. Then I'm going to erase all of this for a second. Well, forever. Let me make sure I didn't have anything else on the screen. No, so that's it. So let me then erase all this. And just note, by going back one slide, that our molecules A, B, and C have different lengths of linker. They have different numbers of carbons. So essentially the boxes are of different lengths. Okay. Also, the number of pi electrons are different in each case, but you can figure those out. So what you need to do is construct the box size, determine the number of electrons, pi electrons, figure out which the HOMO and LUMO are, and then you get your delta E and find your lambda max prediction. And I bet you'll find a connection then between, if we go back to the next slide, between the lambda max trend and the particle in a box. Now, you should not expect exact correspondence between the experimental lambda max and your calculated. I mean, it's probably going to be off by 10 or 20%. I'm not sure how much. The question, because this is a very simple model, I'll ask you to think about what makes that model realistic, but what about it is not realistic? You know, what makes it not realistic? Okay, but it may be good enough to explain the trend. Okay, so that is that is basically the story. So we've now talked about everything that you need to do the experiment and write your lab report. The last topic I want to talk about is something more deep into the theory. It's not required, but I did bring up this quantity F, the oscillator strength, kind of out of nowhere, didn't really tell you where it came from. And that's what I'd like to tell you about now. This is an advanced topic. We will talk about it just a little bit in lecture later on. But since we're talking about F right now, I want to give you some of the background. Here we've got, thinking about the energy levels of our molecule. So these are by the way, not the energy levels of individual orbitals now. These are the energy levels of the molecule, 1, 2, 3, 4. The first one here is the ground state, and then this first excited state up here. And here I've got this transition process, absorption of radiation of, light frequency nu. What does this transition depend on? Now, what does the rate of transition depend on? So what I want you to think about is, suppose you have a large collection of molecules and you're shining light. We're going to consider monochromatic light for now, just frequency nu. So the only excited state accessible is E2 at this frequency. If you have a large number of molecules, then over time, there will be a rate of absorption of radiation. And what does that depend on? It depends on a quantity called mu12. So the 1,2 means a transition from state 1 to state 2. And we call this the transition dipole moment. And I need to talk about it a little bit. It will come up later in class when we talk about spectroscopy in the lecture. So it's this integral. Now I should tell you, this integral comes from formalism, from theory, but it comes from consideration of the time-dependent Schrodinger equation. So we will not talk about that form of the Schrodinger equation in this class, at least we won't solve it. So this is a little advanced, but I can make some sense of this, okay? I think, so we have this integral, state 1 is psi 1, state 2 is psi 2, and this operator is the electric dipole moment operator. So what are we talking about? So let me draw some pictures here. See if we can make some sense of it. So imagine that you've got your molecule initially, happy molecule. I'm just going to write M in a circle for our molecule. And this is, say, initially before there's any light. Okay. This molecule can be in any state. A state is really described by a wave function, so there's a whole set of them, psi sub I. I can be psi 1, psi 2, psi 3, right? So there you go. That's initially. Then along comes a wave function, a photon, or really I should say some light. So now we have our molecule in the presence of light. Now let's draw sort of a classical picture of light. So it's moving in this, that's the direction of propagation, and it's got an electric wave oscillating, electric field oscillating. So that's the electric field in black. Perpendicular to it, of course, is a magnetic field. I'll draw that in blue. Now, this light can interact with the molecule, so the molecule can absorb some light. And so what's the nature of that interaction? Its primary interaction is between is electrostatic. So it's between the oscillating electric field of the light and the electric, primarily the electric dipole moment of the molecule. Okay, that's the majority of the interaction. There will be other smaller interactions, but that's the one we'll consider. So it's the electric dipole interaction we're talking about. If it's possible because of this interaction for the molecule to absorb the light, and then it will be excited to energy level 2, right? This operator right here basically describes that interaction. So we have that interaction operating on psi1. Okay. Now let's consider after the light, is gone. So after the light is gone, we have our happy molecule back again, all by itself. If you like, call that final. That's what I'm going to think about. And the possible states, the accessible states, are the same as before because the Hamiltonian is the same without the wave, without the photon, or without the light. So now initially, we're going to say we were definitely in state psi1. At the end, we could be in state psi1 or we could be in state psi2. We don't know which one. If you have a large collection of molecules, some will be in psi1, some will be in state psi2. And there was a rate. This is a time-dependent process, right? It takes some time. So let's think for a second about this integral, though. Because these psi functions describe the initial or the final state, we call them the stationary states, so to before and after. And the result, shoot, just a second here. So the result of acting on psi1 with this electric dipole moment operator will be some function phi, and phi is a linear combination of the accessible states. In this case, those are only states 1 and states 2. States 3 and 4 are not accessible because they are not the right energy for absorbing radiation of frequency nu. So that's what we have. That's what we have. So now we can now think about the integral. This integral, so the states psi1, psi2, and so forth are orthogonal to each other, or really they're orthonormal. So this is an orthonormal set. So when you substitute the linear expansion in for phi and carry out the integration, there should be a 1 here. The psi1 part simply becomes 0, and you're left with, no, I didn't have them at all. And you're left with just C2. Okay. So that's interesting, right? Now notice what we have down here. It turns out that the rate of transition from state 1 to state 2, and remember you've got a large sample of molecules, and there's a transition rate, and that transition rate will be proportional to this square modulus of the transition dipole moment. So if you think about it, that will be the square modulus of C squared, right? So if you think about it, this phi is kind of, it's really a superposition kind of thing, right? We've seen that before. So we've associated the square modulus of the coefficient in this linear expansion as a probability. So this is very closely related to the idea of probability of a transition. But ultimately, we're really talking about a rate process because this happens in time. So the rate is going to be proportional to this thing squared, which is like a probability squared. Okay. So the question becomes, of course, is this rate large or is it small? If it's large, then we say the transition is allowed. If it's small, we say the transition is small. But what is large and what is small? That's the question. So let's take another look. So to decide whether that is small or large, scientists many, many years ago decided to take a simple reference. They invented a simple reference. And this reference is actually classical in nature. It just serves as a convenient reference. And the reference is, imagine an electron isolated and still. You can imagine it still, if you will. It's a classical picture. And along comes some light. And this is a classical picture of light. The light has some frequency nu. Now we're going to choose the same frequency for our nu as we've got as for the transition in our molecule that goes to state 2. So we're just going to choose that. But anyway, so this light will now, this has this oscillating electric field that will cause the electron to start oscillating with the same frequency because of this electric interaction. So this will definitely happen. The electron will be brought into oscillation classically, and you can calculate a transition dipole moment for the process. And so that square modulus will be what it will be. You can calculate it. Okay, we're not going to do that, but it can be done. So we're going to call this a little OSC down below the subscript. That's for this oscillating electron. That's a classical reference. And now we can define F. So F is defined as this ratio of your actual transition dipole moment modulus squared for your actual molecule divided by the transition dipole moment square modulus squared for this classically oscillating electron absorbing light of the same frequency as your molecule. Okay. Now the electrons one here really serves as an upper limit, because that's a process that definitely happens with a fast rate. But because this is a classical reference, we can't say that the maximum is exactly 1 for this ratio, but it's approximately 1. So that's what this F means. It's called oscillator strength because, well, classically people thought of the light oscillates, so surely the molecule must oscillate in some way when it absorbs the light. So if that molecular oscillation is large, well, what is the strength of that oscillation with regard to the electron? Well, the molecule doesn't actually oscillate, it just makes this transition. But that's the origin of the language oscillator strength. And if F is approximately 1, we say the transition is allowed. But if it's closer to, if it's like less than or equal to 10 to the minus third, we say it's forbidden, right? That really means a fast rate or a strong rate of absorption of radiation by your sample. So that is background. Again, you don't have to understand this background thoroughly to do this lab, but I commend it to your cogitation. And it is advanced, as I said, but I commend it to your thinking, and we'll come back to it later in the course in the lecture.